My name is Gavin Ding. I'm a research lead at Borealis AI. Borealis is part of RBC. We currently have offices across Canada in Vancouver, Waterloo, Toronto, and Montreal. We are a group of about 120 scientists, engineers, and product experts dedicated to bring state-of-the-art AI and machine learning to improve and enable financial services. So today I'm going to talk about Aiden, a reinforcement learning system for order execution. This is our collaboration with colleagues at RBC Capital Markets. I personally participated in the initial scoping of the work, and our colleagues at Capital Markets, including Hasham, David, and Stephen, they did the actual heavy lifting of the work. And I've only listed people that directly contributed to contents of this presentation, but actually there are many other colleagues that contributed to this work. So without further ado, let's jump into the content. So at a high level, Aiden aims to solve the following problem. Say a customer wants to buy or sell a large amount of equity shares. For example, say a Canada Pension Plan Fund wants to buy 1 million shares of Apple close to the current market price. If they put the entire order to the market all at once, then everyone can see it. Then the others on the market will know that someone has a huge demand for Apple shares, and they will increase their prices, and CPP fund will not be able to get the price that they want. So this is where the order execution comes from. So it is the brokerage responsibility to execute this order within a specific time window and seeking good prices that minimize the loss with respect to a specified benchmark. So besides the market impact aspect that we just mentioned, when we execute the order, a naive aspect we also want to consider is to wait until the price is low enough and then buy the shares. But the problem is that given that we need to finish the execution within a time window and given the volatility of the market, how do we know what is low enough and how long can we afford to wait? And after I describe the problem, some of you might already realize that this problem can fit into a reinforcement learning framework. So essentially, we are trying to achieve a certain goal through a series of sequential decisions about how many shares to buy at each time step and receive rewards in the form of low execution prices. And we don't know what is the optimal action at each time step, and which makes supervised learning not quite likely. So in this presentation, I will first describe the order execution problem in more detail, and then I'll give a brief recap of reinforcement learning and describe how it maps to this problem. And then I'll discuss some practical considerations of the design of the Aiden system. So modern financial markets, such as Toronto Stock Exchange and NASDAQ, are limit order markets. So this means that traders who wish to purchase shares can specify not only the volume they wish to purchase, but also the maximum price that they are prepared to pay. So typically, a limit order specifies three things: whether it is a buy or sell order, the number of shares to be traded, the price you are willing to buy or sell. So basically buy or sell, number of shares, and the price. So the limit orders are visualized in this figure, where the horizontal axis indicates the price and the vertical axis indicates the volume. So each of these green bars on the left side is one of the buy orders. Basically, each of them means that a trader wants to buy certain number of shares at a certain price. And we call the highest price that people are willing to pay to buy the bid price. And similarly, we call the lowest price that people are willing to sell the ask price. As you can see, there must be a gap between the bid and ask price. Otherwise, those orders would have already been traded. And we call the average between the bid and ask price the mid price. And this can be used as a proxy of the current price of the asset. So now let's look at what happens when a trader places a limit order. So if the price of the limit order is less than the ask price, then ask price is here, the lowest price that people are willing to sell, then no trade would actually happen, and the new limit order will just be part of the order book. But if the buy limit order's price is at or above the current ask price, then the order will be executed. So the first trades will occur at the current ask price, but if the volume of the buy order exceeds the volume available at that price, then the order will continue at the next price level, which is here. So this process occurs until either the entire order has been fulfilled or it reaches a specific limit. In this case, there are insufficient shares available for sale at or below this specific price, right? And so in this case, because this buy order is large, it will only be partially filled. And this figure shows after the limit has been partially executed. So the remaining green bar becomes the buy limit order with the highest price. So we can see the overall effect of placing a limit order is that the price is guaranteed to be within the specified limit, but the volume you specify might not be traded. And any unfulfilled part of the limit order will disappear in 3 cases. It can either be matched by a new sell-side order, or its time can expire, or it can be removed by the trader who put it there. So this is limit order. There is another type of order called market order, which only specifies the number of shares that we wish to buy. Essentially, this means that we will buy all this number of shares now at whatever prices are available on the sell side of the limit order book. So first, the trader buys shares at the current ask price, and if the volume of the buy order exceeds the volume at the ask price, then the trader will continue fulfill the order at the next price, and so on. So basically, after this, this order disappears, the next one becomes the ask price, right? So this process repeats until the entire order is executed. So effectively, the market order is a limit order where the limit price is plus infinity. And we can see what happens after we place the market order we just showed. So a few of the sell limit orders are executed, and the ask price is further moved up. So after seeing those 2 types of orders, the limit order and the market order, we can discuss the market impact of orders. So if you place a large market order in the market, then you might go deep into the sell order, right? Because you are eating up all the sell orders with low prices, and the price you actually get, the average price you actually get, might deviate largely from the current price. And if you place a large limit order, say something like this, and it won't be executed, but other players on the market will know that you are buying, and then therefore they'll move their selling price higher. So the problem of order execution is to buy a certain volume of shares within a given time window at a good price. And at each time step, the trader can place a limit order, remove an existing order, or place a market order with a certain volume. So for each of these orders, they contain a small portion of the entire volume of shares to minimize the market impact we just discussed. And the information available to the traders include the market history, the number of shares left, and the time left. You can imagine that the trader will adjust their actions based on these information. Say if there's too much time left, but still there is not too much time left, and there is still a lot of shares left, they might behave more aggressively. For example, place large market orders, and by doing this, they'll likely incur a higher cost due to the market impact that we just discussed. So for reinforcement learning to help in the order execution problem, essentially we are trying to train an agent that can make sequential decisions on what actions to take at each time step. And again, these actions include placing a limit order with certain volume and price, removing existing order, and or place a market order with a certain volume. So that is a brief intro of the order execution problem. Let's now do a brief recap of reinforcement learning. So in RL, an agent interacts with an environment by performing actions. It makes decisions on what actions to perform based on the observations from the environment states and the reward it received. The agent goal is to collect maximum amount of rewards during its lifetime. And the most typical reinforcement learning environments are games, for example, Super Mario. So as a human player, I can imagine myself to play this game to collect as many as coins as possible. And to achieve this goal, I need to look at the images, listen to the sound, and perform actions through the controller. And the environment, the game console, will react to my actions by showing the next frame of image and sound. So more abstractly, there are three key components in reinforcement learning. First is policy. It decides how the agent behaves based on the environment states. And in the environment, there are two key functions. One is the transition dynamics. It takes the current states and the action as the input, and then it outputs the next states of the environment. And there is another function that decides how reward is generated based on the states and action, the current states and the current action. So the goal of reinforcement learning is to maximize the sum of the rewards in the agent's lifetime, which is called return. Sometimes we discount the rewards temporarily by adding decaying coefficient gamma. There are a few school of thoughts or paradigms in reinforcement learning. The first one is policy-based. So in this case, you learn a policy. You directly learn a policy that decides how the agent will behave. And basically, it takes an input. It takes the states as an action, as the input, and directly output what the agent should do as the action. Another paradigm is value-based. So instead, it learns a function to estimate the return based on the states and the agent action. And then how you use it is you would maximize your estimated return with respect to the action. So the action, naturally, the action that gives you the highest return is the action that you should take. Another paradigm actually has some overlapping with the previous two is the model-based reinforcement learning. So in this case, you first learn a model, maybe a partial model on how the environment works. Basically, you learn how the environment generates the state and the reward. And then you use the model to do planning to generate actions, or you can perform value or policy-based RL on these models. So deep reinforcement learning is a hot topic recently. And by deep, what people usually means is that they will use a deep neural network to as the model architecture for one of these components. Okay, so after all this background, let's come back to Aiden. It is essentially an RL agent that learns to minimize market impact from large order. And now let's look at the considerations of designing each of these components, which include the action space, the policy, the state or the features, and the reward the learning algorithm will receive. So first, let's talk about the action space. So as we've mentioned previously, the agent needs to make sequential decisions on what type of orders to make or removing an order. And it also needs to decide the price and volume that the order will be placed on. So we can see there are some structures in this action space. So there are categorical variables on what type of actions you perform, and then within some of the action, there's numerical values that you have to make decisions. So this poses a challenge on how the agent's policy can be learned. So in practice, we simplify the action space for the RL algorithm. So instead, directly output these order actions, we choose one from several levels of aggressiveness at a given time step. And then we have an internal system that converts these simplified actions based on each specific orders to actual orders to be placed on the market. So by aggressiveness, I mean how much you want to eat into the other side, right? So when I say most aggressive, the most aggressive action could be a market order with a large volume, right? So then in that case, you will have larger market impact, but maybe you are just short on time and you have to get everything executed. So we call that aggressive. And least aggressive actions would be doing nothing. Say you don't have any orders and you don't want to put any orders. So that's the least aggressive thing. Or if you already have orders, then the least aggressive action will actually remove existing limit orders from the market. For state and features, Aiden's state currently composed of several hundred market features and also self-aware features. So the market features are engineered from market microstructure data. Examples include measurements of liquidity, recent price changes, or whether there is an imbalance between the bid and ask volume. Another consideration on features is generality. This is because the algorithm is required to work in many situations. Therefore, Aiden only use input features that can be found in any market. Moreover, different stocks vary in price, liquidity, volatility, and other quantities. To this end, the Aiden algorithm must normalize the input features to account for the price, liquidity, and volatility variations. So the self-aware features relate to the history of previous actions that Aiden has taken and also the information of this specific order. For example, they might include measurements of how aggressive Aiden has been in recent time steps and how many shares Aiden still has to execute and also how much time is left. For rewards, Aiden is usually optimized with respect to a certain benchmark. And one of such commonly used benchmark is the volume-weighted, it's the volume-weighted average price, or VWAP, over the whole trading period. As the name suggests, this is the average price of all trades happen, weighted by volume. Consequently, rewards are designed based on the difference between the market VWAP and the actual weighted average price that Aiden achieves. Of course, Aiden will not know the market VWAP price until the end of the period, so the reward is delayed, which causes a typical problem in RL, which is the temporal credit assignment problem And we'll need to mitigate this by some practical tricks. So in terms of the reinforcement learning algorithm, we chose to use A3C, which is asynchronous advantage actor critic. It belongs to the actor critic family, where it directly learns a policy, but at the same time using value function to make training more stable. It's asynchronous, which allows parallelization across GPU servers and can handle thousands of client orders at the same time. We also utilize policy optimization, proximal policy optimization to make the training more stable. Another aspect is what environment do we use to train the agent? RL algorithm usually needs to see a large amount of data before they can output successful strategies. And obviously, it's not practical to wait many years for the algorithm to train on the real market. Furthermore, we cannot put the algo into the real market before it has learned to make a decision that performs reasonably well, right? So the solution of both of these problems is to build a simulation training environment based on historical data. So in this way, Aiden can train much faster than real time and learn sensible policies without risking financial loss. This procedure can be further improved by training multiple RL agents who compete with one another in the same simulated market and learn from one another. So to sum up, Aiden is a electronic trading algo that was enabled by reinforcement learning. It has been quite successful and we're performing well during the pandemic and was launched globally in late 2020 and has traded numerous orders for our clients.
Do you fine-tune the model during the past year to account for COVID-induced ambiguous market?
I guess you mean the market will behave differently because people are like the volatility has increased during the COVID time. I think this might be answered by the fact that Aiden is being trained continuously while it's trading, right? So even if there is some market shift, will be adapted fairly quickly to the current market condition. So it's not like it's trained and then we are using it. So it's while we are using it, it's continuous.
Which methods do you use to generate synthetic market data?
So I wouldn't call them synthetic. So it's real market data. And then the thing is that when you have multiple agents in there and you want to do the simulation, right? There are certain tricks that you have to do those buying and selling order matching, as what I presented how the limit order market works, right? So basically, you want to simulate the microdynamics in the market in a, how do I say, in a physical way. By physical, I mean there are certain rules that the exchange follows, right? So you want to simulate those rules in a smart way in order to create how do I say, a realistic microstructure. So it's not like you use a GAN to generate those market data. It's not that there's a lot of domain knowledge involved in that.
How much delay? How does Aiden solve the slippage issue in trading?
It's hard to answer the delay question. I can answer the second one. So the slippage cannot be entirely avoided, right? So the problem of the order execution is that you want to get at least amount of slippage by understanding the market dynamic and behaves. Yeah, so I wouldn't say it's completely solved, but basically the RL's mission is to say for so in the example I gave, we optimize the VWAP, right? So we want to match the VWAP of the market, and the RL's mission is to get as close to the market VWAP, but sometimes it cannot completely reach that goal, right? So and I would say like to eliminate slippage that's not realistic, but our goal is to minimize it.
How much better is this product than other algo trading platforms out there?
There's so many benchmarks that like so many ways you can measure the performance. Yeah, it's certainly better in a lot of scenarios, but I don't think it can be summarized by a single number at this moment. Yeah.